So now we are at a new part where we will talk about the measurement methods for VOCs. So why do we talk about measurement methods? Why? Because we really need, if you are working in, let's say, Al Ain municipality or environmental agency Abu Dhabi, and your task is to make sure that the cement factory is in compliance. How can you make sure? You will get a company to measure their emissions, right? Or they will report their emissions. How are you sure that their emissions that they are reporting is correct? You need some kind of validation to tell you that if I measure it, if you measure it, if whoever measures it, will always get the same value, right? So that's why the EPA has developed these standard methods for measurements for every pollutant, not only for VOCs. VOCs are very tricky. That's why I'm going specifically into them for measurements, and I will show you different methods, and each method really has a philosophy behind it. Why do we use this one and not this one? So the methods that are available for VOCs, we have method 18, 25, 25A, and 21. 18 is used for measurement of gaseous organic compounds emissions by gas chromatography. 25, total gaseous non-methane organic emissions as carbon. 25A, total gaseous organic concentration using a flame ionization analyzer. Method 21, determination of volatile organic compounds leaks. So I'll go one by one, but from the names, what it suggests so far, you can understand that everyone has a different objective. Every method has and every one can be used for a different facility based on really what we are after. So method 18, sample is extracted from a single point at a rate proportional to gas velocity. So here we have the gas going up the stack, and we are collecting the gas at a specific flow rate. The organic components in the samples are separated by gas chromatography, and the separated compounds are analyzed with a suitable detector. Now this, once you get the slides, this you can find the actual method itself. Very complicated, very long. It's not really for you to learn, but I just want you to understand how it works and get the essence of it. There is a job called stack tester. Stack tester, it's a very common job in air pollution. So this is the job of the guy that goes up on a ladder or goes or very sophisticated things. They go up on a crane, and he goes with his equipment and sticks the probe and goes down in the computer and keeps everything to measure the flow rate, measure the gas concentration, and then puts it in a report. Just for you to understand the magnitude of things. A regular measurement, how much do you think it could cost? Like if you are a facility and you want to take one measurement, VOC measurement, come up with a price. Up. It could go up to $60,000 to $80,000. Dollars, not dirhams. Leash. Very good question. The equipment, the reproducibility, the guy who makes this is very skilled in taking the sample, and then the lab that does the analysis. It's very not all the methods we'll see now. Not all the methods you measure while you are there, but some of them, like this one, you collect your sample and you take it to the lab. So there'll be further analysis, and for the lab to get the certification and to make sure that what I'm saying is correct, this also costs a lot of money. Plus the crane, plus there is a lot involved. So, well, sometimes it's, I'll show you right now, the different trains you take for the sample. But yes, it is very surprising. It is very expensive business and lucrative business. So there is a lot of money involved. So now we're talking about gas chromatography. I'll tell you in a second what is gas chromatography, but I just want you to take a look at this picture over here. This is what a gas chromatography looks like. We have several of them in the lab, in our labs here. This is specific one is fitted with something called MS detector, mass spectroscopy. So, and I will explain to you what exactly that is in a second. So, but this is just what I want you to understand, that this consists of two parts. The GC, which is gas chromatography, this is this orange one, and the detector that could be different types. And this is, and in this picture I was telling you, it's mass spectroscopy, that's the detector. And all of this is connected to a computer where you can get a signal to read the concentrations. Okay. So when is this method applicable? For measurement of about 90% of organics emitted by industrial processes. Now, keep in mind, not all VOCs always can be measured with the same method. So some of them can, some of them cannot. So this method covers like about 90%. Detection limit is about 1 parts per million. Remember the 1 part per million, we were talking about it at the beginning of this class. Does not include techniques to identify and measure trace concentrations. So 1 ppm is not very small, by the way. We have the ppb, the ppt. We still have a whole ranges of concentrations below that. So 1 ppm is really considered as a large concentration in environmental engineering. Will not determine compounds that are polymeric, can polymerize before analysis, or that have very low vapor pressure. So this method does what we call speciation. Speciation means that it tells you the concentration of the specific compounds. So it can tell you the benzene is this much, the toluene is this much. Sometimes we don't want that. We want the total. We don't really care about what each individual VOC is. Sometimes we want to know the specific compounds. So this is the one that gives you the specific compounds. So when you are sampling, you have to have pre-survey sampling techniques. So because it's very expensive to sample, you need really to understand what is the range of concentration that I'm looking for when I go to sample. Is it high concentration? I can just get it right away and do it. Is it very low concentration? Because the method goes down up to 1 ppm. So do I have lower that I'm interested in? So I need to take some other techniques to make sure that the concentration is enough for my measurements. So there are lots of things that we can do, including evacuated or purged glass sampling flasks. So we get flasks like this that don't have any gas. They are vacuum and they are high vacuum. So that once you connect them to your stack, they fill right away. You can have flexible bags, what we call Tedler bags. This flexible bags is a very similar concept to balloons. You know the balloon, the party balloon that you blow in? So the Tedler bags are the same thing. So they are normally flat, and then here, like what you see in this picture down there. And once you start connecting them, then they start to fill like a plastic bag or a balloon. They don't stretch like a balloon, but they just fill until you get specific pressure inside, and then you close and you take it to the lab. Or you get something called adsorption tubes, like this one over here. So this is where the pollutant goes from one side, or the airstream goes from one side and goes out from the other side. But within this, the pollutant is taken with some solid media inside the tube, so it stays inside. And then we can reintroduce it for analysis in the lab. So very sophisticated techniques for how to collect your sample. It really depends on what you want. There is no good or bad. So for example, if you have high concentrations, then you can use the flexible bags because they are the cheapest. The bags are just very simple concept, right? You're basically trapping thing in a plastic bag and take it to the lab for measurements. Now, if you have some of the pollutants with very low boiling point, so basically they escape very quickly, it's better to use the evacuated or purged glass sampling flasks, because the vacuum will make sure that they stay inside. Because when you have very low boiling point, they tend to escape very easy. So you want to make sure that they stay in your flask and you don't lose them before you sample them and measure them. So then this becomes, at low concentrations, the tube are the best, because you can pass as much air as you want to accumulate more and more of the material that you're looking for. So again, every method, so that's why you need to know what you are looking for in your industry.
So if I don't know what the VOCs are in the site, then go.
Well, if you really don't know, usually you try to do cheaper tests just to let you know what you are, where you are. And then you go for the actual testing. Because look, there is compliance tests and there are non-compliance tests, meaning that you can do a test that's not really very well controlled, so it's much cheaper, but you will not use that to show compliance to the regulation. You are just using this for information. But you can do as much, and it can be the same test, it can be different tests. But then when it comes to compliance, that's the very important one, that every step has to be very well documented, very right, and so on, because this number, when it goes to the regulatory agency, they need to trust it. So then when you go, you have different ways to do the sampling. You have direct interface, dilution interface, absorption tubes, or flexible bags. Direct interface, meaning that you have a measurement that you can, the GC, that you can put right at the stack. So you can carry the GC to the stack and take the measurements on the spot. Okay, so has advantages and disadvantages. We'll talk about this in a second. If the concentration is too high for the detector, you might want to dilute it to bring it down, so the detector it's not saturated with all your compounds. So then we have what we call dilution interface. So you're taking it from the stack, and then you are diluting it with some gas, and they go together to the GC and the detector. So now we can measure within our good range. Or you can take it to the lab with adsorption tubes or flexible bags, or also the canisters that we talked about. So direct or dilution interface sampling, the strength is there is no loss or alteration of compounds, because really you are taking the sample right there. So coming right from the farm to the, like how you're eating from the tree, right? So there is nothing will happen to the tomatoes in the way there is it's very fresh. method of choice when temperature is below 100 Celsius and VOC concentrations are suitable. So weakness is that the GC, the GC, the gas chromatography, must be located at sampling sites, and you cannot sample proportionally or obtain time integrated sample. Meaning that now, if I have a bag, I wanted to compare the two scenarios. If I have a bag, I can sample over 10 minutes. I can take sample for 10 minutes that I keep getting the sample over the bag. Now I'm averaging this 10 minutes when I am measuring it, right? So now it's all the 10 minutes are in the bag. So when I'm measuring it, I'm actually averaging everything that was there in the 10 minutes. Let's assume, let's assume that if this is time on, and this one, sorry. Let's assume that the x-axis is time and the y-axis is the concentration, and we have the concentration going, and this is, by the way, very typical for a factory. You don't have stable concentration that's going all the time. Why? Because you have machines, you are adding raw material, now you have a lot of concentration, now the concentration goes down, goes up, depending on the temperature. Now the engine started to run, you will have more. So a concentration in a factory is very, very much changing. So when we want to take measurement, we are actually taking a picture in time. So we are basically taking here, or we are taking at one point. So when you are taking the direct or dilution interface sample, basically what you are doing, you're taking really a picture in time for a specific time. You cannot collect a large sample and take an average. While with the tube, you can let the concentration go through the tube. This will average it out. Or you will collect everything within a bag. This will average it out. Do you guys get the concept? For a tube or a bag, you are basically measuring an average, time average. While if you are doing direct or dilution, you are taking a one time shot. Depends what you're looking for. If your stream is more or less constant, you can take the GC, the direct in the site. But if it's changing too much, you actually want to know what's the average, because it might hurt you. I might take a sample when it's here at the high peak. Then I am not in compliance, right? Questions? So absorption tube sampling works this way. You have here your stack. This one is your stack, the blue one, and you have a probe that goes usually inside the stack. This is applicable for everything. So the stack is you know the stack you see in a lot of factories. So you will have the opening where you stick the probe inside, and then you will have a filter. Why do you think you have a filter? Yeah, but what are we filtering? What do you think is important to filter out? Particulates. Sometimes liquids, but the most important is particulates, because the particulates will block your tube, right? So you get a filter to block particulates, and then the gas will go through. There is a pump that does suction. So just to make sure that the flow goes here is controlled. So now you know what is the flow that's going here. And because this flow will really be a part in the calculation of the concentrations later on. So over here in the green section, the pollutant or the VOC will keep getting more and more stuck to the surface of the absorption tube. You do it for a preset time, maybe 1 minute, maybe 5 minutes, maybe an hour, depending on your pre-survey. Okay, and then you take this one to the lab. This is, for example, how it looks like. Could look like that. It could look a lot, it has a lot of different shapes. Any questions? Yes. If we leave it for it really depends. If the initial concentration is really low, you might want to leave it for a very long time. So that you collect enough for analysis. So show. Right? But if the concentration is high to start with, the whole thing can get saturated in no time. Once it's saturated, you cannot really use it. Let me for this point, because this is very important. Once it's saturated, you cannot use it. And we'll get to it, inshallah, in the next chapter when we talk about absorption specifically. But if the tube has a specific capacity, once you exceed the capacity, you only know that it's larger than the capacity. You don't really know what is the concentration. Because once it exceeds the capacity, whatever goes in goes out. The tube will not collect it anymore. So once you exceed the capacity, you only know that it's larger than this much, which is not really helpful. So you always need to be below the capacity. Yes.
It's more likely that we should use plastic valve rather than the absorption.
Correct. So the media that's being used inside the tube can be one of these or more. There are always new advancements in adsorbent media. Activated carbon is very common adsorbent. Silica gel, 10X, XAD resin. They look different. This is carbon, the one on the left, the black one, or the one on the right. This is the silica gel. This, for example, here is another example of adsorbent out of glass. You will have here the two tips where the flow will go through it. Here is in the middle is the adsorbent layer. And you see this one here has a detector for breakthrough. What is breakthrough? Breakthrough happens when you exceed the capacity. So when you exceed the capacity in this one, it starts to show you that it exceeded the capacity. So this is not valid anymore. You have to discard it and start again. Okay? Yes. So the absorption tube sampling, the strengths that the samples are compact and easy to handle. You can return them to the lab for analysis. Can be stored up to a week at 0 Celsius. The weakness of the breakthrough capacity must be known. Again, this is a very important point. Effect of moisture must be known. Now, when we set the filter, we said, yes, that it's for particulates, but if you have moisture in your sample, it will definitely affect the capacity of your tube. So we need to know how much moisture there is to account for it when we are talking about the capacity. But also, it cannot really be used if you have too much moisture, because the water will just come and fill all the pores and nothing will stick on the surface. And again, also it builds a pressure. So quantitative recovery of compounds must be known. So let's, and maybe this will be more clear when we go through the adsorption and I explain to you what is adsorption. But once you collect all the compounds on the surface, you have to reintroduce them, right? For measurement. When you put them for measurements, you have to make sure that they leave the tube so you can measure them. Now, compounds, similar to how they get to the tube in a different manner, they also leave the tube in a different manner. So you need really to understand how they do that, qualitatively and quantitatively, because it makes a very big difference. Samples must be collected at a constant rate. So let me just, before we go to the last one, so let me just give you an example. Now, let's say we know that benzene will leave the tube at a temperature of 200. If I go only to 180, I will measure everything else except benzene. So I need to know that I have benzene, and I need to know that I have to reach the target temperature where it leaves the tube, right? So now let's assume that this pen is the tube. Now I got on it, adsorption tube. I got on it 3 VOCs, benzene, toluene, and hexane. Okay. Now let's say when I want to measure it in the lab, I will take this tube and put it in the instrument. So what will happen? I have to make sure that the benzene leaves the tube, the hexane leaves the tube, and the toluene leaves the tube. But every one of them leaves at a different temperature. I have to heat this tube to make them leave. They don't just leave. So now I'm assuming that benzene has the highest temperature for leaving the tube. If I only go to a temperature lower than the required temperature, the hexane will leave, toluene will leave, but benzene will still be there. Now I am reporting a false sample because I'm reporting there is no benzene. However, there is, but I just didn't account for it. You see why it's so expensive? Because there's so much stuff that's you have to be aware of while you are doing this sampling.
Temperature that they leave
That's why you have to know this is specific for every adsorption material. No, it's not different. The boiling point affects it, but it's not the boiling point. So it has to, you have to overcome the forces that attract this molecule to the surface. We'll get into this a lot details, inshallah, in the next chapter when we talk about adsorption. Okay, so, but however, we just want to make sure here that we know that we have to account for a lot of things. So this is very difficult to make sure that you get everything right. Yes. So samples must be collected at constant rate. So why do we have to collect samples at constant rate? I said that a minute ago, because if you have different rates, you will not really know how much is your concentration. Because finally, you let it run for 5 minutes, you let it run for 10 minutes. What the mass that you collect, the mass of pollutants that you collect on the tube is a function of the flow rate. If you have double the flow rate, you will collect much more sample. If you have less flow rate, you will collect less sample. If you have varying flow rate, you will never know what's your. So everything is connected. So the flow rate has to be really constant in order to compare apples to apples. Make sense? The flexible bag sampling, remember I told you the Stedler bag is like a balloon. So this is the stack wall. And you put your probe inside the stack wall with the filter, glass wall, that's for particulates. And then you connect your bag to the probe You fill your Tedler bag. Sometimes we put the Tedler bag in a leak-proof container to make sure that when the bag expands, it doesn't rupture. And we can also apply vacuum on it to make sure that the flow rate of filling the bag is constant. So we can see here that there is a pump, vacuum line, and vent. And here we can also have like a manometer just to check the pressure within the stack and so on. So you're starting to get the complication of doing stack testing.
So we measure the pressure in the stack.
Yes. But also the pressure will, together with the vacuum that you have outside, will determine the flow rate that's going. You want to know this flow rate and you want to regulate it. So the higher the pressure, maybe you will have to lower the vacuum and so on. So strength samples approximate from the stack samples are returned to lab for analysis. Samples may be collected proportionally. The weakness are the bags are awkward and bulky and prone to leaks. So I remember one of my students had like 20 bags and the plant was like 6 hours away. That was in America. And by the time he came to the lab, we had 12. The rest were punctured. The rest were, yeah, they were flat. Something happened to the bags. Basically, it's very challenging to do that. Compounds may absorb onto the bag surface. That's another problem. Now, how the tube works, remember now we're going step back to the tubes, that the tubes attract the VOC and they trap them inside, right? Similarly, the surface of the bag may be, for some of the VOCs, may be a good surface for them to attract and attach to. So we might be already, yes, we collected all the sample and everything was fine. But when you want to reintroduce it, you are actually leaving something behind in the bag. Make sense? If you have a device where you can heat the whole thing, you can put the bag in the oven and heat it and then collect it well. You can do that, but you also have to know which compounds to reach the required temperature. Not very easy. You might as well, if you know that it will absorb, you might as well choose a bag material that will avoid this attachment. Storage time is generally less than 24 hours. So once you collect them, you have to go back and you have to test them right away. Why? Because compounds also can react with each other or get affected with the sun while they are being transported. That was another thing that, well, because of this long transportation, we had to make the van very dark so that the samples do not change while you're being transporting them from the factory to the lab. In the vacuum, well, if there is any leak, you are actually putting extra pressure to pull the gas out of the bag. There is always a problem. So now we collected the sample. So we took it to the lab and we want to measure it. There is chromatography, what I called you the gas chromatography concept, is a concept where you have columns that look like this picture here. They have some material inside, very similar to the idea of the tubes, but on a much smaller scale. They have material inside where when you put a gas stream of different compounds, the yellow, orange, and red, they will go inside at different path, and they will come outside at different times. So, for example, here, the yellow will come the latest, the orange will in the middle, the red will come so fast out. So basically what we are doing, we are taking a very mixed stream and we are getting it out in different compounds, one after the other. It's a separation technique, yes. This is what the chromatography is. In general, any chromatography. There is gas chromatography, there is liquid chromatography, there is ion chromatography, there is the chromatographies are, and it's a whole branch of study. There is people that study analytical chemistry. That's all what they study. For us, we just need to know how they work, general idea. So that if you are a stack tester, you know what's happening. If you're an engineer, you know where are the shortcomings. That's why we're studying this. So what we know from the chromatography now that we have the benzene, the toluene, the hexane. Remember the three that we used as an example earlier? They come all together. Now I know that benzene is coming alone, hexane is coming alone, and the toluene is coming in. So in gas chromatography, we have the column, which has this material inside. This is where the separation is happening, okay? So this part here is the actual separation. So in order to really have our sample to be separated, we have to have flow rate and a constant flow rate. So in that, we use a carrier gas. The carrier gas, I can make the flow rate as much as I want. I can set it at 1 meter cube per second, 0.1 meter cube. I can do whatever I want. And I usually use a carrier gas, one of the noble gases. Remember what are the noble gases? They are the ones that don't react. So the carrier gas will go this way into the column. While they are going, I will introduce my sample. Where is my sample? Either in the bag, either in the tube, flask, whatever there is, but I will introduce it inside this carrier gas. So now the gas is mixed, the carrier with my sample, and goes to the column. If there is no sample, whatever goes in goes out, because it's a noble gas, right? But now that I have a sample that have three different VOCs, we will start to get them out at 3 different times. 1, and then 2, and then 3. And then it goes to something called the detector. What happens inside the detector? The detector sees what they call disturbance in the force. Remember Star Wars? Disturbance in the force. That's, anyways. So basically what happens that I see temperature that is 20 degrees, and it's 20, 20, 20, and then the hexane comes. Suddenly the temperature, instead of 20, becomes 30, and then goes back to 20. Benzene comes, 40, go back. Toluene comes, and so on. That temperature could be a detector. There is a detector called thermal conductivity detector. It could be electrical charge, ECD, electrical conductivity detector. It could be electrical charge coming from burning of the compounds. That's the FID, flame ionization detector. There are so many detectors out there. Every company is doing innovations in getting detectors that go to lower and lower concentrations. One of the very sensitive detectors is the one that I showed you in the picture earlier, which is the mass spectroscopy. So this basically breaks down the elements into its smaller forms and measures the molecular weight of the smaller forms. It's very, very sophisticated equipment. And then after the detector, it goes through a recorder, which is probably a computer that's connected to your GC that gives you this type of peaks. The carrier gas itself is the baseline. It does not make any disturbance. So let me show you here. You see from here, for example, this is the carrier gas alone. This is the carrier gas alone. The carrier gas itself does not give a signal. So it gives a signal actually, but we estimate that as our baseline. So we zero at the signal of the carrier gas. It's always there, and even without before the sample. So we know the baseline, and then start to, you get these peaks, like peak number 1 here, peak number 2 here, and so on. Here, 3, 4, and you keep getting these peaks. These are disturbances of the field. And based on the area under the curve, you can estimate the concentration. The larger the area under the curve, the more concentration there is, because that means there is more disturbance. Make sense? So the idea itself is easy, but the implementation really hard. It's not like a household device where you press a button and then you get things out. It really requires very sophisticated measurements. So I'll stop this video, and next video will be about method 25, and we'll do it inshallah next class.